Hello, good morning everyone. I am Dr. Abdul Pasha, Assistant Professor, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Here it is about the course Power System Operation and Control. So in this I am going to give presentation on voltage and reactive power control problems. So this will describes about some numerical examples based on voltage and reactive power control case. Earlier videos you have seen that how voltage control is achieved and the reactive power control, how can we manage, what are the various methods, various strategies developed to control the voltage and the reactive power control, what is its importance in line compensations, how they can rectify the distortions in the lines, compensate for the voltage case and reactive power case. These are the issues we elaborated earlier case. Now this will describes about numerical analysis. We will take some simple examples and based on that we will elaborate the problematic chapter here. So here the first example is about a consumer's load, that is about 250 kilowatts, has a power factor of 0.78 lagging. So power supply charges are 50% per kVA of maximum demand. This should be per month plus 0.5% per kilowatt hour. So cost of power factor is by the improving operators, which is considered in US dollars, that is 10 rupees per kV. And the rate of interest and depreciation is about 10%. What extent the power factor should be improved so that amount saved is maximum. And also it is asked to calculate kVA capacity of the power factor. kVA capacity of the power factor, that is as improving apparatus. So this is the diagram describes about kVAR capacity of the power factor and how the old kVA and the new kVA comparisons with respect to the real power coefficients. So here power triangle is drawn as triangle OAB. This internally have another triangle OAC also. So these are the two triangles representation. So OA term, that means OB will represent old kVA. And here OC will represent new kVA of the line. Old kVA and new kVA is generated from the system. And only OA will represent real power in kilowatts. Real power in kilowatts. They are supposed to be differed by an angles of phi1, phi2. So here the change from C to B or B to C, kVAR capacity of power factor, that is treated for improving apparatus. Whatever the change we expected in this boundary, this will be the kVAR capacity of power factor for improving apparatus case. So with this analysis, we will treat one of the cases, that is power factor 1 as cos phi 1, that is 0.78 lagging, and power factor 2 as cos phi 2. This is mostly economical in nature, and the real power is about 250 kilowatts, and the reactive volt amperes capacity of power factor for improving operators will be treated as P into tan phi 1 minus tan phi 2. Cost of the power supply is given, that is 0.5 US dollars per kVA, and the cost of energy is 0.05 US dollar per kilowatt hour. Cost of the apparatus is 10 US dollars. Interest and depreciation is about 10%. Annual charges for power factor improving operators can be treated as 1 of the A multiplied with I by 100 into P into tan phi 1 minus tan phi 2. So with this, saving by the improving of the power factor is U into P by power factor 1 minus P by power factor 2. This may be treated as consumer's gross saving. So consumer's net saving becomes this D coefficient minus B coefficient. So to maximize this, as ds by d phi 2 is considered as 0, so dd by d phi 2 minus db by d phi 2. That is u into p tan phi by 2 into secant phi by 2 plus a into 1 by 100 into p secant phi square into secant phi square r sin phi 2, which is a into 1 by 100 by, which will be gives about 0.2, and cos phi 2 will be obtained in 0.97 lag, that is the lagging power factor. So usually we require leading or unity condition, but when it is getting lagging condition means capacity of the power factor improving operators becomes P into tan phi 1 minus tan phi 2. So what is the P value? Actually 250 kilowatt into tan phi 1 minus tan phi 2. So calculating for tan phi 1 and tan phi 2, finally we will get 127.62 in kVAR. So this is the solution obtained as capacity of the power factor in improving operators. Next problem is like this: 3 supply points A, B, C. A, B, C are the 3 supply points. A, B, C. Supply points. They are connected to a common bus bar. They are connected to a common bus bar. That is M. Supply point A is maintained. This is the supply point A is maintained at a nominal 66 kV, and it is connected through a 66 by 33 kV transformer, about 0.1 per unit reactance X. That means X value is 0.1 in per units, and 33 kV line of reactance. So 33 kV line of reactance, that is X, will be 20 ohms. Supply point B. Here supply point B is nominally at 33 kV and is connected to M by 66 by 33 kV transfer. So this is about 0.1 per unit reactance, and 33 kV line of 20 ohms reactance. So if at a particular system load, the line voltage at M falls by 5 kV, calculate the magnitude of the reactive voltamps injection required at M to re-establish the original voltage value. So per unit values are based on a 100 ME baseline. So this is the problem given actually. So the system adopted here based on the given parameters. A and B are the one of the busbar units. They started at 66 kV line with 1 per unit, that is 66 by 33 kV, which is connected by 20 ohms resistors onto the line. So M point is representing with the 20 ohms. So here from sending end is 66 kV, receiving end is about 33 kV. So this is stepped down, and with this 20 ohms resistor of 1 per unit value, 66 by 33 kV, the distribution is done here. When 66 kV is supposed to be coordinated at C point, then MVA AB becomes 100 and XB in 33 kV circuit, that is 10.89 ohms. So reactance as in line case is about 20 ohms and per unit value becomes 1.83. So with these coefficients, we can calculate transformer reactance as 0.1 per unit. Reactance about M2A is 1.93, M2C is 1.936, all are in per units. Parallel combination of XA and XD are 0.968. Reactance from M2B is 1.83. Equivalent M2N is 0.634. So fault MVA at M is equal to MVA by equivalent reactance, that is 157.72 in MVA case. And the fault current is fault MVA multiplied with 1000 by 1.73205 into 33, which gives a current about 2759.501 amps. This may treated at 0 power factor leading. So delta in QM by delta VM gives 1.73205 as multiplied with fault current, that gives 4779.594 reactive volts amps per volt. And if you consider in MVARs, this becomes 4.77 MVAR per kV. So drop in voltage at the line will be 5 kV. Now reactive power required becomes 23.89, which are in MVAR case. So these are the parameter values that will be calculated as in the manner of drop in voltage and reactive power required. Next problem is when two units of the generators, they maintain 66 kV line to line and 60 kV line to line, same at the ends of the interconnected inductive reactance, that should be per phase about 23.09 ohms and with a negligible resistance and shunt capacitance. So it is about a load of 12 megawatts is to be transferred from the 66 kV unit to other end. So calculate the load angle across the interconnector and the power factor of the current to be transmitted. So this is the line diagram, VS, VR. So VS is at an angle of delta and they are connected by the line JX. So here VS at an angle of delta minus VR, phi by JX. Here Vs cos D plus JVS sin D minus VR by JX. So complex power becomes VR into I, which are in conjugate in nature. VR Vs sin delta minus JVR into VR minus Vs cos delta by X is going to be treated. This is entirely the sum of complex power coefficients which are in conjugate nature. So real power coefficient can be calculated with VR Vs sin delta by X. And the real power coefficient is given about 12 megawatts. Source voltage applied becomes 66 kV and receiving end voltage is about 60 kV. With this we will get reactance about 23.04 ohms. Then sin delta will be calculated as Px by VR Vs. Then with this coefficient it will be calculated as 0.069818. So when you taken in a delta case, that is 4.003, which are in degrees, and cos delta becomes 0.997. So tan phi is minus Vs cos delta plus VR by Vs sin delta, and that is about minus 1.26778. This is tan phi. And cos phi is 0.61931 lag. So this we already obtained. Next problem is single phase motor connected to 400 volts 50 Hz supply that takes 31.7 amperes of current at a power factor of 0.7 lag. Calculate the capacitance required in parallel with the motor that is ready to raise the power factor to 0.9 times. So here the problem is given for the single phase motor that is connecting to 400 volts applied with the frequency 50 Hz. And the supply takes 31 amps of the current and the power factor is 0.7 lagging case. Here we need to calculate the capacitance required in parallel with the motor. This is ready to raise the power factor to 0.9 lag. So here 400 volts 50 Hz supply is treated, that is with IC and C. C is connected across the supply and motor combination is treated here as IM equals to 31.7 amps. And with this the power factor coefficients becomes IC and IM. So splitting coefficients are as the sum of the vector combinations. They are differed by an angle of 90 degrees and that phase difference is denoted with phi. So this is from A to IM. This is the reference voltage. So with this the cos phi is about to obtain as 0.7 and we can calculate phi m as cos inverse of 0.7, that is 45.4, and sin phi m becomes sin of phi m value 0.714. So cos phi m is 0.9 means phi m becomes cos inverse of 0.9. Then phi m value is about 25.84. Sin phi m becomes sin of this 25.84 gives 0.435. Active component Im becomes Im cos phi m, where Im is about 31.7. That is already given. With this cos phi m is 0.7, that is already we are having from above relation, that is 0.7. So this product gives 22.19 amps and active component of I, that is I equals to I cos phi. So I into cos phi means I can be calculated here. We already have the active component of I. So 22.19 by 0.9 gives 24.65 amps. Similarly, reactive component of Im becomes Im sin phi m. That is Im is 31.7, sin phi m is 0.714. So the product relation gives 22.6 amps of current. So reactive component of I is I sin phi. That is 24.65 under root 1 minus this power factor square cos phi square. Sin phi means here sin phi becomes under root of 1 minus cos square phi. So here cos square phi value is substituted 1 minus 0.9 whole square. So I is 24.65 and this becomes 0.436 as 10.75 amps. So IC is here reactive component of IM. So reactive component of I we will obtain 22.6 minus 10.75. That gives about 11.85 amps as V equals to IXC, X equals to 1 by 2 pi FC. Then IC becomes V by XC. So V into 2 pi FC. Here with this, this becomes 11.85 is equal to 400 into 2 pi into 50 into C. So by this C is 94.3 into 10 power minus 6 farads. So this is the value of the capacitor we required to calculate in parallel with the motor. This is ready to raise the power factor at 0.9 lagging case. Another problem is given here. Alternator is supplying load of 300 kilowatts at a power factor of 0.6 lagging in nature. If the power factor is raised to unity, how many more kilowatts can alternator supply for the same kVA load? So kVA here is equals to kilowatt by cos phi. Then kilowatt value is given as 300. So here what he is asking, as the load is supplying, power factor is lagging in nature. Here power factor is raised. that is about to 1 unity. How many more kilowatts can alternator supply? That is asking for the same kVA load. So kVA becomes kilowatt by cos phi. Kilowatt is 300, cos phi is 0.6. So 300 by 0.6 gives 500 kVA. So with this condition, as P is VI cos phi, which is in kilowatts, Q is VI sin phi, which are in kVAR, then S becomes VI, that is kVA. So kilowatt at 0.6 power factor gives 300 kilowatts. Similarly, kilowatt at 1 power factor gives 500 into 1, that is 500 kilowatts. This will be increases the power supply by the alternator. And kilowatt at 1 power factor, that is 500 minus kilowatt at 0.6 power factor. That difference gives you total 200 kilowatts of the power. Here another problem, single phase AC generator supplies the following loads. One is a lightning load, that is 20 kilowatts at unity power factor. Second one is induction motor load, about 100 kilowatts at 0.707 lagging. Third one is synchronous motor load, that is about 50 kilowatts at 0.9 power factor leading. Calculate the total kilowatts and kVA delivered by the generator and the power factor at which. So here kVA 1 is ready to calculate, that is kilowatt 1 by cos phi 1. Kilowatt 1 is 20, cos phi 1 is 1, then it is about 20 kVA. So kVAR 1 is equals to kVA 1 sin phi 1. So kVA 1 is already given 20 kilowatts into sin phi 1 means, which is 0, that is 20 into 0 means kVAR 1 becomes 0. kVAR 2 is kVA 2 sin phi 2. kVA 2 is minus 141.4. So with this multiplied with the sin phi 2 means 0.707. So this quotient will give minus 100 kVAR. With this kVA2 calculation becomes kW2 by cos phi 2. So that is 100 by 0.707. That is about 141.4 kVA. Similarly, kVA3 is kW3 by cos phi 3. That is 50 by 0.9, which is about 55.6 kVA. So kVAR3 becomes kVA3 sin phi 3. So 55.6 into 0.436. This quotient will give 24.3 kVAR. Here noting that kVAR2 and kVAR3 are in opposite directions. So kVAR2 are being a lagging while kVAR3 being leading in kVAR case. So total kVA kilowatts becomes 20 plus 100 plus 50, that is 170 watts. Total kVAR becomes 0 minus 100 plus 24.3. So minus 100 plus 24.3 means minus 75.7 kVA. So total kVA is equal to under root of kilowatt whole square plus kVAR whole square. So kilowatt whole square is 170, kVAR whole square is 75.7 whole square. That is 186 kVA. So finally power factor achieved becomes total kilowatt by total kVA. That is 170 by 186. When you cancel each other, 0.914 lagging power factor we will obtain. So power factor must be lagging since the resulting kVAR is lagging in nature. That should be lagging in nature. Coming to the next problem case, 3-phase 50 Hz 400 volts motor develops 100 HP, power factor being 0.75 lagging and efficiency being 93%. So here a bank of capacitors are connected in delta across the supply terminals and the power factor raised to 0.95 lagging. So each of the capacitance units are built to 4 similar 100 volts capacitors. Find the capacitance of each capacitor. So original power factor is given as cos phi 1, which are 0.75 lagging. Final power factor is cos phi 2, 0.95 lagging. Motor input can be calculated as P equals to output by efficiency. That means we know that efficiency equals to input by output. So from this 80 kilowatts obtained, phi 1 becomes cos inverse of 0.75, that is 41.41 degrees. Tan phi 1 is tan 41.41 degrees, which is 0.8819. Tan phi 2 becomes cos inverse of 0.95, which is 18.19 degrees. Tan phi 2 is tan of phi 2 value 18.19, that is 0.3288. So leading KVR takes by the condenser bank is P into tan phi 1 minus tan phi 2 case. So 80 into tan phi 1 is 0.8819 minus 0.3288, which is equals to 44.25 kVR case. So leading kVRs taken by each of the three sets becomes 44.25 by 3. So that is 14.75 kVR case. So with this consideration, phase current of the capacitor is calculated as ICP equals to phase voltage by reactance, capacitor reactance, that is 2 pi FC V phase. 2 pi into F means 50H. Capacitance can be calculated here by the condition 50240 of the capacitance value about one of the leading KVR gives C equals to 14.75 by 50,240. That will give 293.4 into 10 power minus 6 farads. So 293.4 microfarads. Since it is the combined capacitance of 4 equal capacitors joined in series, so capacitance of each capacitor becomes 4 into 293.4, that is 1173.6 microfarads. So by utilizing that capacitance of the capacitor, we may treat that amperes. 1.25 kilo farads, that is in micros, will obtained as amperes. So KVR per phase is V phase I phase by 1000. So V phase is 400, I current is 1.25, which are in capacitance range by 1000, which will give this value 50240 C. Another problem is two generating stations A and B are linked by a line and two transformers of total 20 ohms refer to 132 kV and a negligible resistance, load of 100 megawatts, 0.9 power factor lagging is by the bus bars of A and B. So here 200 megawatts for B, 85.85 power factor lagging from B. So find the phase angles between the bus bars A and B, the voltage adjustment required to equalize the load on each station. So initially both stations have bus bar voltage 11 kV which are in phase. Solution is here P1 and P2 with this two bus bars AB. PA will be the power at the point of A and PB will be the case at point of B. With VA and VB are the two voltages. Real and reactive power coefficients are determined as reactance value is 20 ohms and first power coefficient is 100 megawatts. Second power coefficient is 200 megawatts. With this, the phasor diagram can be drawn as with respect to VA and VB, the power angle delta may be derived as Jx1 coefficient and this difference is delta V. The current drawn will be here and with this delta V we can adjust the set required value. So P1 is about 100 megawatts, power factor 1 is 0.9 lakh case and Q1 is P1 tan power factor 1 of the particular region, that is 48.432 in MVAR case. P2 is 200 megawatts, power factor 2 is 0.85 lagging. Q2 is P2 tan ACOS by power factor case, that is 123.9 MVAR. So to equalize the load on each station, that means A and B, PA, PB, we need to equate to 150 megawatts. So P becomes PA minus P1, 50 megawatts. QA becomes Q1 plus Q2 by 2, 86.19 MVAR. As we calculate Q, QA minus Q1 is considered. Your loss is ignoring as I into IX in the whole line. Then this difference becomes 37.75 MVAR. So from the phasor diagram, delta V becomes X into P phase by PB. So reactance becomes 20 ohms. Per phase voltage is 76 kV. and per phase power becomes 16.6 megawatts. Delta V is 4.37 kV. So as the from the diagram phasor case here, we should derive that the condition sign delta becomes delta V by VA, which is delta V by VB 0.057392, as delta is 3.291799 degrees. So bus bar A is 3.29 degrees in advance of bus bar B. So delta V is XQP phase by VA phase. So Q phase as 112.586 MVAR. VA per phase is 76.21 kilowatts. So delta V is XQ phase per V phase, that is 3.30 kV per phase. So with this combination 5.72 kV line to line is obtained, as 5.75 increases on 132 side of the A. So these are some of the references whichever I have considered. So here the problematic involves with power coefficients are going to be interchanging with respect to the line parameters that we must treat, and according to that the solution may be generated. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.